Next up, we have some anatomy lessons from shaders given by Timo Heinapurola, so let's give him a big hand.
Okay, thank you very much. So I'm going to talk about shaders. And the way I'm going to do that is, first I'm going to go through a history lesson of shading, basically. And we're going to go through the different graphics cards that from the 19th century to the modern day. And basically, that's sort of like to show how we've come to this point. After that, I'm going to go through the graphics pipeline, as documented by the DirectX 11 SDK, and followed by a description of how the GPU actually works. And I'm going to use the AMD GCN architecture actually as a reference there. But before we start there, I might introduce myself. So my name is Timo Heinapurola. I work as the lead programmer at Bugbear Entertainment. Currently lead the development of the NCG project, Next Car Game. I have about 13 years of 3D game engine development experience, most of it as a hobby, basically as a very intensive hobby, actually, and some, of course, at Bugbear, and also I have some entrepreneurial experience as well in the gaming industry. And I've worked in the IT industry, so rather broad spectrum of different kinds of things for programming. And now to the actual topics. We're going to look at the early days of graphics cards now. I just wanted to really explain how we've gotten to this point and show that from how primitive starting points we've actually come from. So the first notable generation of 3D acceleration cards was probably in the 1995 to 1996 when we got the S3 VIRGE, ATI Rage 3D, Rage 2, and Voodoo cards. It was just simple rasterization and texturing, really no geometry processing on there. And for instance, the Voodoo card was actually very simple. The first card actually had just 3D rendering on it. So you actually required a secondary 2D card to do 2D rendering on there. And the Voodoo Rush card was later then introduced, which actually incorporated a 2D unit basically glued on top of that. But the card was very slow, and in 2D and 3D, due to basically the bandwidth problems that were resulting from that module. Then in 1999, we got the Geforce 256, which was basically coined as the first GPU graphics processing unit because it had a transform and lighting pipeline built into it. So most of the work actually done previously on the CPU could now be offloaded onto the graphics card. So here we actually started seeing, this graphics processing on a separate graphics card. And had DirectX 7 support. But the problem here was that even though it had transform and lighting, it wasn't really very performance, this specific card. So if you had a CPU, a rather good CPU, and a just rasterizing graphics card, then you probably had better performance than you did on this card. With Geforce 3, basically, in 2001, we finally got VERTEX shaders and pixel shaders, so a lot of more, really the ability to do a lot more complex vertex processing and pixel processing on there with the added programmability. With GeForce FX and the Radeon R300 series in 2002 to 2003, we then got support for DirectX 9 and more complicated shaders, basically. There were, of course, a lot of API improvements on there, but those are probably like the most, the improved shader, the shader model 2 and such were really important there. Then we got the R600 and GeForce 8 with DirectX 10, with its geometry shaders. Personally, I think that geometry shaders have they're useful, yes. You can generate like fins and fur with them, but really the API changes that came with DirectX 10 were remarkable in my opinion, because you were able to create these objects, these immutable objects that could be validated before you actually use them. So they were used just by binding those objects, and you were sure that you were able to use them. So then, basically, improving on that, we got DirectX 11 support by the next generation of graphics cards in 2009, and here's pretty much where we're now. So we've improved from basically not having any geometry pipeline whatsoever on the graphics card to actually having these supercomputers that we have nowadays for the PC, even mobile, and even within your car, basically. So that was like, you know, a fly-through of what actually has happened here. And now we're going to look at what actually makes the GPU tick. And for this, we're going to go through the graphics pipeline as documented by DirectX 11 SDK. This is mainly to connect the talk about the hardware that we're going to also look at with the actual programming interface. And also at the end, I'm going to make a note about general purpose computing, because that is a very hot topic nowadays in games development as well. And I hope that, even though many of you probably are very familiar with these topics, I hope you get something, at least some specifics, some good information out of this. So, the pipeline. Basically, this is like, you know, the general picture of the pipeline. Here you have the different stages of the pipeline. The brown ones are the non-programmable parts, which are basically just parameterizable. And then you have the shader parts, which are nowadays fully programmable. These are the vertex shader, the hull shader, domain shader, geometry shader, and pixel shader. And the hull shader, tessellator, and domain shader form the tessellation stage, basically. All of these, almost all of these stages use memory resources as well. So this is a very high-level picture of the pipeline. And we're going to look at each of these stages separately. The primitive assembly stage is basically, it's parameterized, so it's not programmable pretty much in any way. And its purpose is to build up primitives. So it receives as its input the index data, the vertex data, and basically what kind of primitives you're going to render, how you're going to read the input layouts and stuff like that, how you're going to read those vertices and actually generate the renderable geometry. It can also provide adjacency information as of DirectX 10, which basically means that it provides information about, for triangles, for instance, adjacent triangles, and you can use that information to do different kinds of extrusions and stuff like that. We're going to cover that in the geometry shader part later on. It also generates semantics. So you have information like vertex ID, instance ID, if you're using instancing. So that's generated by the input assembly stage as well. So this is the starting point into the pipeline, generates the primitives. The vertex shader stage comes next, and it's executed at least once for each vertex, and it outputs a single vertex. Example techniques that could be used here: skinning, very primitive displacement mapping. We're going to look at the tessellator stage later on, and that's actually a better place to do displacement mapping. But you can do texture fetches, for instance, and offset your vertices using those values, samples of those textures. Then you can do simple vertex sliding, for instance, or compute any kinds of values that are that you want to interpolate over the triangles, and that can be done on the vertex shader side and should be done for optimization purposes. The vertex shader. It's executed once per each vertex, at least once. With that, I mean that actually the input assembly stage, or the hardware stage representing that, has a vertex reuse buffer. So basically, you're gonna want to order your indices so that you will use this reuse buffer, basically. So if the the input assembler basically sees that there's a vertex that has already a memory process, and it's located in the reuse buffer, it's going to use that vertex instead of actually executing the vertex shader again. There's place about for like 14 vertices or so in the reuse buffer, so you should be really careful about how you lay out your primitives for rendering. Next comes the whole shader stage, which is a very new stage in DirectX 11. It's the first part of the tessellation unit. And it receives as its input 1 to 32 points, a single patch, and it outputs the transform control points of the patch, tessellation factors that control the next phase, stage, which is the tessellation stage, and it also outputs patch constant data. So this information stays constant over the whole patch. Yeah, so basically this prepares the tessellation unit to do its work. So next comes the tessellation stage. This is, again, not programmable. It receives as its input the patch and the tessellation factors. It's executed for the patches to split them into smaller objects. And the splitting is actually done in a canonical domain in a normalized coordinate system. So for instance, if you have a unit square, then it's going to be tessellated in that unit square. If you have a square, it's going to be tessellated in a unit square. Simple. And it outputs UV and W coordinates for the domain shader. The domain shader basically takes this information and the data from the whole shader, and its purpose is to generate the final vertex position for the vertex for which it's called, basically. Places or techniques that could be implemented in the domain shader are, for instance, displacement mapping. So once you have split the geometry into these smaller pieces, done tessellation on it, you can then do displacement mapping by basically sampling a texture and offsetting that new vertex in its normal direction, for instance, or whatever you want to do basically there. So then we have the geometry shader stage. The purpose of the geometry shaders is basically to, now that gets a bit annoying. Well, okay, anyway. The geometry shader is executed for each primitive. So it receives all the vertices of the primitive as its input, as well as optional adjacency information if requested. And this information is actually not available if you're using tessellation. So it's only usable if you do it the traditional way without actually using a tessellation unit, just rendering triangles and be done with it. The outputs are primitives of a chosen type. They're always strips, so whenever you generate triangles, you're going to generate triangle strips on there. Example techniques are, for instance, fur that you can generate, and shadow volumes, for instance. Excuse me. Okay, the stream output stage comes next. So this is basically the stage where you can output your generated geometry, or post-geometry shader geometry, basically. You can output it back into the vertex buffer. So you can do a pre-transformation of vertex data for, well, if you can basically do anything, compute anything on geometry pipeline and just output it into vertex buffer. So it's usable for some cases. The rasterizer is the next stage. The purpose of the rasterizer is basically to generate pixels. So it receives the geometry from the previous stages of the pipeline and converts them into pixels, basically. And it determines how the pixel shader is executed for those pixels. And then we have the pixel shader stage. It's executed for each pixel. It receives the interpolated primitive attributes as its input, and it outputs a color and optional depth value multiple colors if you have MRT, being multiple render targets. Example techniques: per pixel lighting. You can have very complex per pixel lighting and isotropic lighting using textures as your source. You can do parallax mapping here, so basically tricking the eye to actually seeing a paving, for instance, somewhere on the street. You can do ray traced fog as well, for instance. Then we have the output merger stage, which basically generates the final pixel color. So it takes the pixel shader output and uses the pipeline state, does depth stencil testing and blending, and is not programmable. So now we've come to the end of the pipeline, and now we're going to look at how the hardware actually works, how it actually does the stuff defined by the pipeline. We're going to use the AMD GCN architecture, being the graphics core's next architecture, as a reference. And basically what it's all about is that these are massively parallel systems. So you have a huge amount of cores on there, and emphasizes vector operations, because it's really vector operations are everywhere there. You have positions, you have normals, you have colors, you have matrices, you have quaternions, you have all kinds of stuff that's actually defined in vectors. So it's logical. It shares a common shader core, or shares common shader cores that it uses as its workhorse. And there's a set of hardwired logic that basically then controls how these cores execute the instructions. Okay, so the AMD GCN architecture is structured so that it contains multiple compute units. For instance, the Radeon HD 7970 has 32 CUs. So that's quite a lot, really. Each CU, each compute unit, has 16 arithmetic logic units that each can execute one instruction, or that can execute one instruction for 16 work items, or basically data points, each cycle. The sim actually, its resources as well. One point about the resources of the sim, they're basically separated into two groups. They're shared and private resources. The private resources are the ones that the sim owns, so it's not shared with any other sim. They're instruction buffer, registers, and vector arithmetic logic units. Then there are shared resources, like the front end, which controls the execution, back unit, branch unit, and the data cache. The rendering itself is coordinated by the graphics command processor, and basically the subsystems that actually do rendering are basically the front end, the rasterizer, and the back end. So we're going to use those terms. I've seen different terms used, but we're going to use these. So we're basically operating on wavefronts, or it's a very central topic here. Wavefronts are actually, they consist of 64 work items. You can think of a single work item as a single vertex or a single pixel, for instance. Each sim has an instruction buffer for a maximum of 10 wavefronts. What it actually fits really depends on how many registers your program is actually consuming, and how much different kinds of resources it consumes. So it might be below 10, and usually for a pretty typical kernel, it's going to be under 10. Okay, so then we go to the instruction fetch. Basically, this is the stage where the CU chooses which SIMD is going to receive an instruction. And 4 different CUs share a single L1 instruction cache, and it has bandwidth enough to satisfy all these 4 CUs in each cycle. And which SIMD actually then receives or can fetch an instruction depends on each priority parameter, and the utilization of its wavefront buffers. Yeah, I have a few numbers about the instruction cache, if someone's actually interested. It's basically 32 kilobytes in size. It's four-way associate and backed by an L2 cache. Each cache line is 64 bytes long and typically holds 8 instructions. And it's least recently used eviction. So it's going to evict the cache lines that have not been recently used. So here you have a diagram, basically, of what's happening here. So it chooses each one of those SIMs to actually do the fetching and does that from the L1 cache. So after we've fetched the instructions that we're going to execute, we have to decode them. So the process of decoding goes so that the CU actually does round-robin fashion, actually goes through the different SIMs in a round-robin fashion, choosing one SIM at a time to do decoding. Each individual SIM can decode 5 instructions per cycle, but each of these instructions must be from a different wavefront. And this is basically to make sure that we're doing in-order execution. Also, they have to be of different type. So different types, there are 7 different types, but a few are branch, scalar ALU, or memory, or vector ALU, etc. But basically, if you have 10 wavefronts, you're going to, per SIMD, you're going to have some wavefront that you can execute instructions from. Yes. So here's basically what happens. So the SIMD, the CU chooses one SIMD per cycle going in a round-robin fashion, and each SIM then does decoding. You also have the scalar unit there depicted. The scalar unit is the separate unit that also can do, is mainly concentrated on control logic and has 2 separate pipelines that have specific purposes for that, but mainly control, flow control. So this, I wanted to talk a bit about VLIW scheduling as well, because this is what was done before. And there were problems with this kind of architecture, which basically resulted in the creation of the graphics cores next technology. It superseded GCN. Yes, it was technology used before that. But the problem really with VLIW was that you had to, the compiler had to actually look at the code and find 4 to 5 different instructions that it could co-issue. So basically, the structure was very different. It has 16 different lanes. Each lane could execute 4 to 5 different instructions per cycle or per clock, and these had to be from the same wavefront. So basically, the compiler had to find out which instructions were co-issuable and then co-issue them in the pipeline. And this works for graphics because you have a lot of operations going on in pixel shader, vertex shader that can be parallelized in a simple way. But for general purpose computing, it just didn't cut it. So that's why this architecture was developed further to provide what basically now is using the GCN architecture. Another problem was port collisions, for instance. The wavefronts had to be aligned so that you had instructions not colliding with each other in the execution pipelines in terms of the ports that were, registry ports that we were using. So this is basically an illustration of what is actually happening here. So the VLIW had a single SIMD with 16 different lanes, and each lane had, I'm depicting four units here, but it can do 5 at a maximum. You basically had 4 different instructions they're running in parallel. But the GCN does it so that it has 4 different SIMD units, each of which has 16 ALUs, each executing a single instruction on 16 data units, work items. And a couple of words about the memory of the GCN, because I think it's interesting because it has cache coherence, which is a great thing for general purpose computing. Cache coherence basically means that it has the L1 and L2 cache, yes. So it uses the L2 cache, which is shared by the different CUs, to keep all the L1 caches coherent. So previous architectures had to rely on programmers explicitly pushing the modifications in memory into main memory so that other CUs would see that. But now it's basically handled for the programmer, so the programmer doesn't have to do anything. Simplifies really the development, the way development is done. Also, the GCN has basically an x86 based virtual memory system, which paves the way for unified memory between GPUs and CPUs. But currently, it's also a very good way. It simplifies the copying of memory from CPU memory to GPU memory, even if the memory is not shared per se. So from the graphics point of view, the front end is basically what assembles primitives. So it's pretty much like the input. It's basically the input assembly stage on the hardware level. So it assembles the primitives and controls basically vertex transformation. So it issues the wavefronts for vertex shaders, geometry shaders, and so on. Tessellation actually, that actually might be controlled by different unit, but there's, it depends on where you actually group that unit. But I have it here. This unit also manages the vertex reuse. So it basically looks at which vertices have already been transformed and reuses them for future triangles. And yeah, and you want to use index buffers, by the way. So if you're not using index buffers, you're just drawing polygons by you have in DirectX 10, you have this draw primitive up. User pointer, where you just send the vertices without using any indices, then you're not going to be able to use the vertex reuse buffer. So use indices. Then we have the rasterizer, which maps directly to the rasterizer in the DirectX pipeline. Basically, receives the shaded vertices, primitive indices as its input, information about each triangle. It performs rasterization, basically does position transform to screen, does front face, back face culling, area culling, view frustum culling, and it generates the wavefronts for the pixel shaders. So it controls, this physically controls how the pixel shaders are executed. It sets up the wavefronts for execution, or the sim units for execution. Then we have the back end, which is basically pretty much like the output merger state or stage. It pretty much maps to the output merger stage. It performs depth testing, stencil testing, alpha testing to generate the actual, to determine the fragment visibility. And samples the shaded pixels for coverage and color, and then does alpha blending to determine the final pixel color, and outputs this to the frame buffer. And as a side note, the backend actually uses, or the CU has basically these export registries that are used for writing into the frame buffer, or for where they're used to communicating between the compute units, the SIMs, and the fixed function pipelines, and are also used for outputting, the vertex colors, pixel colors, and stuff like that to frame buffer. Okay, so there, basically we have how the graphics pipeline works. And I wanted to say something about general purpose computing, because it's a very big thing nowadays, even in game development. You have a lot of applications using general purpose computing for post-processing and for different kinds of physics simulation, stuff like that. It comes from the fact that most of these algorithms actually require massive parallelism as well. So it's very well suited for this. And as with GeForce 8, with the generalization of graphics computing, we were able to extend this graphics processing power to general purpose computing. And I've listed 4 different technologies that are used nowadays. The first one on my list is CUDA, which is the NVIDIA Proprietary technology. It's a C++ language, C++ type language, but supported natively only on NVIDIA hardware, but also provides NVIDIA-specific features as well. For instance, the Kepler architecture has this thing called, the newest architecture of NVIDIA has this thing called dynamic parallelism, where you have the ability to conjure new work on the GPU without actually going back to the CPU. So, it's good for if you're relying on NVIDIA technology. Then you have OpenCL, which is an open standard maintained by the Kronos organization, supported by the NVIDIA and AMD architectures. And it's a good choice, in my opinion, for if you're starting from scratch to build a general purpose computing system. Then you have C++ AMP, which I specifically find very interesting. It's actually a standard, even though it's been developed by Microsoft. But hey, the .NET framework is a standard as well. It basically allows the execution of C++ 11 lambda expressions on the GPU. So what the compiler does, it converts actually these lambda expressions into code that can be executed on the GPU, and it uses then a backend that basically does this compilation and execution. Then we have a very related technology, compute shaders, which are basically in the newest iteration and can be used in DirectX, Microsoft-specific technology. So compute shaders, they rely on executing kernels. Kernels are basically programs written in a GPC, general purpose computing language. They use a grid-based execution setup. So you have these work items and you have work item groups. Work items are, for instance, if you want to work on a grid, it doesn't specifically mean that you're working on a specific item on the grid, but you are working sort of like on a representation of that item on the grid. The kernel is then executed once per each work item. And as I said, on NVIDIA, you can start new jobs, new work, basically on the graphics card. And they incorporate a lot of technology really nowadays to build these massive servers. For instance, the Kepler architecture has copying of memory from card to card that are actually resident in different server rooms or different servers, and it can communicate with NOS servers and stuff like that. So there's really, really a lot of work being done in the GPU side. It's a really interesting field. And for games development as well, I wouldn't disregard that technology, and really there's good use for that. Okay, so basically that's my talk. And I hope you've enjoyed it. Hope you've got some information at least out of it, especially the hardware side. And if you have any questions, you can ask them now, or if you want, you can send me an email. You can follow me on Twitter. And also, I blog at the AltDev blog. Basically, a very active game development blog. So, any questions? If there are no questions, then thank you very much.